Hi students, I hope you've got my message that we're not actually going to have an in-person class meeting for today on Friday the 24th of January. Instead, for this class, we're just going to refer to a lecture video. Unfortunately, I had a meeting come up that I'm not able to get out of, and so we're not going to be able to meet together today, Friday the 24th of January. Therefore, just looking ahead at these announcements, the quiz that we were going to have today on Friday will instead be scheduled for Monday the 27th of January. So on Monday, when we get together again at our normal schedule, in our normal location, in person, live, on Monday at the beginning of class, we'll have that quiz, our first quiz of the semester. Also, in the announcements here, you can see that homework number 2, which is related to cash flows, compounding, and other topics, that's still going to be due, as originally announced, on Friday, December 31st. So that homework assignment is available now. I'd encourage you to get an early start on it. There's a lot of things that you could have already started on based on class number 4, and then today's in-class exercise and lecture topics will also feed into that same assignment. So get an early start. The subject of today's lecture is on compounding, and I've emailed you the in-class exercise paper that accompanies this lesson. So I would encourage you to print out that in-class exercise so that you have the paper there in front of you. During certain parts of the recording, you need to pause, and so that you can run your calculator and try and solve the problem. Don't just watch the solution and copy down the solution, but actually try and attempt it yourself. That's the best way that you're going to absorb and learn and retain the information. Now, I should mention that this recording that you're going to be watching, the bulk of it was recorded in a previous semester, and so there may be a handful of incidental references to times or things that I said in the past that don't quite match up since it's from a previous semester. But what will match up, all the content is still the same. The concepts haven't changed since that previous semester. So these announcements that you see here on the slide and that I've announced via email, these are the ones that govern. So if you have any questions, please feel free to send me an email. I'd be pleased to hear from you, and I'm always happy to help if you have any questions related to the homework. Otherwise, enjoy this lecture on compounding, and I will see you again in person, live on Monday the 27th of January.
This is one of the in-class exercise problems that we worked in class on Wednesday. I see many of you have 3-ring binders. I hope you're saving these because I really do think that they're useful as a resource for the assignments, quizzes, exams. So at the end of class, we kind of ran out of time, and I wasn't able to show you how we could also solve this using a spreadsheet. Now, this is just one of those first taste ideas that I want to show you right now. And so don't feel like you need to follow along with Microsoft Excel as I show it to you. Don't stress out if it seems a little bit confusing right now. This is maybe like just how you get inoculated against diseases, you know. They give you these shots. This is your first shot on seeing how we solve problems like this with spreadsheets. And so just follow along with the table and see if the numbers make sense. What we have in the table is the first column is the year. And of course, we have some interest rate that is accounting for the time value of money. And there's nothing in row 0 because nothing's happening at the present. It's not until the end of the first year. Remember that each one of these segments between the lines represents a duration of 1 year. So from 0 to 1 is a 1-year period. The beginning of that 1-year period is the present, 0. The end of that 1-year period is 1. So 1 marks the end of the first period. Okay, so there is inflow to us, 12,500, and it's an annual series. And so that's why each of these 12,500s is the same, and there's 4 of them. Okay, so that's the first 2 columns here. The next column is saying previous balance. And previous balance is saying, how much did you owe the bank at the end of the last year? And so at the end of the first year, how much did you owe the bank last year? Well, we didn't owe the bank anything yet because we hadn't yet received any of those installments to us. At year 0, nothing had happened, and so it says 0 because our previous balance due to the bank is 0. And so the question then is, how much of this amount that's the amount outstanding is subject to the 5% interest. And so it's how much do you have to pay to the bank? It's how much they've given to you and also any previous interest. Because remember, what we talked about in the compounding lecture is that not only do you pay interest on the principal, but you pay interest on interest. And so it's a way for the banks to make more, or if you're an investor, it's a way for you to make more compounding interest. And so how much do we have to pay interest on? It's just the $12,500. And so at the end of the period, and so year one, at the end of the next period, you have to pay $625 of interest. And so then the cumulative amount owed at the end of the second year is $13,125. And so then that number, the $13,125, goes here on row 2 where it's saying previous balance. So when you receive this second installment of $12,500, so they give you $12,500, and in the back of the banker's mind, as he slides that money across the table, here's your new $12,500, he's thinking, how much does this guy owe me? He owes me the $12,500 that I just gave him, and he owes me $13,125 because he owes me the $12,500 from last year and the interest on that amount. And so now the banker's thinking, well, this year I'm going to earn 5% on the combined total, $25,625, and that interest amount is $1,281. And so then at the end of this current period, you've got $26,906. So if we go through that same process of thinking, how much are you earning, how much interest is accumulating during each annual period, then at the end it's $53,877. And that's the same number. If you look back in your notes, you'll see that $53,876.56 is how much the amount was when we did it kind of the graphical approach. You know, like the graphical approach was we're moving this arrow 1 to 3 years into the future. We're moving this arrow 1, 2 years in the future, you know, where we were just shifting money amounts forward in time, and so then they were compounding according to the factor 1.05 to the n, where n was the number of years. Okay, so is everybody with me? This is just something we're going to do eventually. We're going to do it this way, but not today. Wanted to tie it together with what you saw in lecture last time. It's all kind of interrelated and building. Okay, well, let's talk a little bit more about interest. Simple interest is where you avoid the effects of compounding and you're only having to pay interest on the principal. And you're not likely to see a simple interest loan in your life unless it's someone who really likes you. Like maybe your parents would give you a simple interest loan, but certainly I wouldn't. I like you, but not enough to give you a simple interest loan. The bank doesn't like you that much. They want you to pay interest on the interest. But a simple interest loan just says there's some principal, the amount you borrowed, the number of periods, and then the interest rate per period, and that's how you calculate the interest amount. So for instance, let's say that some rube is making a loan of $100,000 for 3 years at simple interest of 10% per year. So the repayment amount then is 100,000 is the P, the N is 3, and 0.10 is 10% per year. And so 30,000 is saying you don't have to pay interest on the previous years. It's just on the principal. So the total due would be the principal of 100,000 and the interest amount. So that gives you 130. So I wonder, how much is this person leaving on the table by not asking for compound interest? Like how much more could they have got if instead of agreeing to a simple loan, what if they had asked for interest on top of the interest? Well, let's look at that. A compound interest is the principal plus all the previously accrued interest is what you have to pay interest on during each period. And so that's compounding over time. Think of it, your problems are compounding. You know, things are getting worse. It's growing, snowballing over time. And so the formula that tells us the interest during a certain time period, this formula looks pretty complicated at first glance, but it's not. It just says in a certain year t. So maybe if t is the third year, then the way to figure out how much interest you owe in year t is by looking at the principal of the loan and all of the interest from previous years. So any interest from year 1 until t minus 1. So remember, if t is 3, then what you'd say is the interest that's due in year 3 is the principal amount plus the interest from year 1 and the interest from year 2, all of that combined and then multiplied by the interest rate I. Okay, so this formula is not so complex, and let's look at a specific application of it. That $100,000. Now this person's more savvy, so instead of agreeing to a simple interest loan, they want compounding interest. And so it's the same $100,000 for 3 years at 10% per year. So let's look at in year 1, at the end of that first period, then the interest amount is $10,000. The total balance due is $110,000. So far so good. But in year 2 is where things get interesting, because the interest amount of 10% is not applied just to the original principal of $100,000. No, in year 2, the interest is due on the entire combined $110,000. And so the interest amount that year is $11,000, and now you can see that the balance is $121,000. So then year 3, the 10% that you have to pay for the privilege of borrowing this money, it's 10% of the total balance up to this point. It's not 10% of the principal. And the total balance up to this point is $121,000. And so it's $133,100 by the end of that 3-year period. And so it's an extra $3,100 into the pocket of the person providing the loan, compared to the earlier example we saw of 10% per year simple interest. So the effect of compounding can make a difference, especially if you let it go for 20 or 30 years. Can you think of any kind of a loan that goes for 20 or 30 years? Mortgage, equipment, sometimes people's student loans can last that long. And if you look at the total amount paid on $100,000, even at a low interest rate, like, like a good mortgage rate is maybe these days 3.5%. So what's 1.035 to the power of 30? Anyone with their calculator help me out? What is it? 2.76. So what that means is that if you paid $100,000 for a house when you bought it, over the years of that loan, you're going to pay the bank $276,000 for that $100,000 house. And that's when the loan is 3.5%. That's really low rates. You know, credit cards can be in the 19, 20, 25%, and they want to convince you to pay the minimum amount due, because they know that if someone just pays the minimum amount due, that hamburger you got from Wendy's for $5, in the end, over the course of financing it for 12 years or whatever, it's going to be like quadruple or 5 times as much as the original purchase price. So don't fall into the trap. Okay, so here's the formula. Who can tell me what this formula allows us to calculate? The interest rate for a given year. This isn't the total interest rate over the entire duration of the loan. It's just in the year in question. So the T means for a certain year. It's not the interest for the life of the loan. Okay, so just for instance, how would we apply that equation for the interest amount in year 3? Well, up above, we saw that the interest amount in year 3 was $12,100, according to our step-by-step procedure. let's just check and make sure that that formula would give us the same thing. So P, 100,000, and then the sum of the interest amounts from j equals 1 to j equals t minus 1. So from the first year all the way to the second year. So that means we're going to have two interest installments, the 10,000 installment, the 11,000 installment. We add it all together, and 10% of that's the 12,100. And so yes, it matches up. The formula, this formula would tell us the interest amount for a given year in the same way that this step-by-step approach, 1 year at a time, will. So it's easy to do this year-by-year approach if we've only got 3 years. But think about a 30-year loan and 12 months per year. So that's 360 rows. And so this formula would be useful if you wanted to know, what's my interest payment going to be in 25 years from now on the 11th month. I don't know why you'd need to know that, but this will tell you specifically for a given year how much interest it is. Any questions about this illustration? All right. We're going to compare two different ways of describing interest rates, because banks are crafty. As I've already hinted at, they really are always looking for a way to get you to agree to a loan that's to their advantage rather than to your advantage. And one of the ways they do it is by misdescribing how much interest you're going to have to pay or how much they pay to you. And one of the ways they get away with it is this language, nominal versus effective. Does anybody here know what the word nominal means? Okay, so exactly right. What he said is if you measure something that's 0.995, then that's pretty close to 1. So nominal means almost. I think of nominal as not really. It's, 0.995 is not really 1. And so when a bank tells you their nominal interest rate, that's not really the interest rate. You need to calculate the effective interest rate. So nominal, what they do is if the interest is compounded on more than an annual basis, the trick is that they'll report it on an annual basis. And so, for instance, let me give you some specific numbers to highlight it. 16% per year compounded quarterly. So they make it sound like you have to pay 16% per year. But it's not really 16% per year. The effective interest rate is higher than that because of the effect of compounding. And so what we're going to do is take a look at what's the actual effective interest rate in a situation like that, where you're taking into account the compounding over time. And so the formula I'm going to show you for the effective interest rate says that we have to look at the nominal interest rate, R. And so in our brief illustration, R was 16%. 16% is the nominal interest rate per year. So that's 0.16 nominal. So remember, not really. It's not really 16% after we do the effective conversion. Okay? M, the number of compounding periods per year. In this previous example, it was quarterly. How many quarters are in a year? There's 4 quarters in a year, just like there's 4 quarters in a dollar. So a quarter is 3 months. So M is 4, so that's the number of compounding periods per year. Okay? Any questions so far? Is there something going on out there? Come on in. Everyone's welcome. We've got a couple of seats in the back, right? Okay. All right, so let's just do the substitutions here. So I is 1 plus 0.14. Can I help you?
I'm looking for the science and biotech building.
That's that way, down the street.
Is it one more block?
Yep, one more building over.
Thank you.
Yep. 0.16 divided by 4 to the power of 4 minus 1. Okay, so what we're saying is it's 1.04 to the power of 4 minus 1. Does everybody see that? All right, so it is 1.16986 minus 1. So what's left over is 0.16986, which is 16.986%. Okay, so what was their trick? They tried to get you to agree to a loan that they said was 16%, but effectively it's really almost to 17%. Those sneaky devils. So what do you think the bankers do when you are depositing money? Are they going to tell you about the effective interest rate or the nominal interest rate when you're putting your money into a savings account? They want to tell you, all of a sudden, they change the tables and they want to start talking about effective interest rate, and they call that APR, the annual percentage rate. And so if I'm looking for a new savings account and they say, hey, we have 2.4% interest rate paid monthly, but it actually doesn't work out to 2.4% unless you reinvest your interest. If you're withdrawing your interest, and some people live on fixed income instruments like CDs or bonds or whatever, it's only actually the interest rate they say if you reinvest the earnings. So you got to always be on the lookout for the bankers. Any questions about this conversion between nominal and effective interest? Okay. So we're going to work through an in-class exercise today that has some compounding questions on it. And the formula that we're going to use for most of them is I'm going to ask you to calculate a ratio. And so the ratio just tells you how much, how many times more the future amount is compared to the present amount. Now, what I suggest you do, just to start thinking of these as a ratio, because there's also table lookup ways to solve problems like this where you don't use an equation, but you just look up a factor out of the back of your book. Actually calculate, when you have f to p, it's going to be some number. Actually calculate that number before you move the p over to the right-hand side of the equation. So in other words, before solving for f on its own, calculate the ratio. Just so you can see, like here I told you that 3.5% interest over 30 years at essentially 2.76 times the original amount. So on each of these problems, I'd like you to just take a look at what's the effective factor that is applying to calculate the future amount. All right, so let me hand this out. I hope nobody here has family working at a bank. Here I am trashing bankers all the time. I'm sure there's not. Your mom? Well, she's probably one of the good ones. She's changing it from the inside, right? All right. Thank you. Let me pause you for just a moment and interrupt with a couple of ideas, and I've had some good questions as I was walking around I want to share with everybody. Okay, the first thing I wanted to illustrate is One way that you can break down these word problems and make sure that you're interpreting it correctly is to label the variables right there on the page next to the numbers themselves. So for instance, you deposit $25,000. That's a P. That pays 6.5%, I. So I'm kind of labeling what I'm going to later on do the substitutions right there near the text. Okay, now people are asking, well, isn't this factor, f divided by p is 1 plus I to the n, isn't that the same thing as the equation that I showed you in the past? And it is. In the past, I just said f is p 1 plus I to the n. So why bother not jumping straight to that? And the reason why is I want you to see this ratio, like the 6.6143. Next week, you're going to be looking up factors like this out of a table. And I want to have you understand or have a sense for where these factors come from. It's like in the back of your book, they've pre-solved these formulas for a lot of different n's and a lot of different i's. And so there will just be the result of that calculation as a factor in the back of the table. So, there's nothing mysterious about how they did it. I just wanted to show you that you can do it too. You can calculate these factors. And so the factor 6.6143, that's the ratio of the future value to the present value. So $165,359 is 6.6143 times as much as the original 25,000. So it's a multiplier. One last thing is be sure to carry through all of the precision in your calculator and don't round off. Otherwise, your answer won't be accurate to the nearest penny. So for example, if you had just said 6.61 and then you multiply 6.61 by 25,000, then you won't get exactly the same thing as the number that I have boxed in there. And we want to, whenever we can, be accurate to the nearest penny. Okay, so you can resume working on that in-class exercise. I'll scroll down to show also the answer to question 2 and 3. And if you have any question about that, you can raise your hand and I'll come around and we'll discuss it. Okay, I have the solution to number 4 up on the screen if you want to double check whether you have that. And I put some text at the top too, kind of to reinforce what this all means. It's not just enough to plug numbers into an equation. Engineers have to understand the fundamentals, the concepts why it's that way. So what I wrote there is that the main idea is that, for instance, using A as an illustration, receiving 6% per quarter is effectively the same as 26.25% per year after the effect of compounding is factored in. And so the effect that we're talking about with effective interest, the effect is the effect of compounding, paying interest on top of interest, not just on the principal. That formula in problem 6 is a ratio. You know, this equation on the right side, that's A divided by P. So calculating that will give you the ratio of the annual payment that is required for some certain present value. So the ratio of A to P at a given interest rate and for a certain n number of periods.